Hello, everyone, and welcome to today's webinar. My name is Beth Capellas, and I'm the Sales and Support Manager here at Triangle MicroWorks. Thank you for taking the time and joining us. Today, we will be talking about establishing a vendor-independent specification process to support top-down engineering of IEC 62050 systems. Before we get started, I'd like to go over some housekeeping items while everyone is still joining. The webinar is scheduled to be 90 minutes long. The audience is on mute, so please submit your questions online using the webinar toolbar under the section titled Questions. You can submit questions as soon as you have them. We have several folks monitoring the questions and responding to them directly. We will answer questions at the end of the webinar and are happy to stay on longer if questions continue to come in. Next, I'd like to introduce our speakers. First, we have Thomas Sturks, expert in virtual substations at Elia Engineering. Thomas has worked at Elia since 2014 with a focus on 62050 system engineering and modeling. He is also a member of 62050 Working Group 10 in C-Grade B568, as well as co-editor of 62050-90-30 and 7-6 Edition 2. Next, we have Yannick Tiesso, Engineering Project Manager at Elvexys, a Swiss company within Condis. Yannick has over 15 years of experience, known for designing innovative and robust solutions for data management, engineering of energy transport and distribution networks in Europe. Yannick specializes in Helinks STS, a 62050 vendor independent system configuration tool, and serves as a key figure in training and user support. In addition to his role as product manager for customized client versions of Helinks STS, he oversees standardization projects for TSOs, DSOs, and integrators. Next, we have Jackson Moore, application engineer at Triangle MicroWorks. Jackson received degrees in electrical engineering and computer engineering from North Carolina State University and has a background in power system engineering. Prior to joining Triangle, Jackson worked as a microgrid system engineer, where he aided in the design and development of control systems for multi-source microgrids. In his role of application engineer, Jackson serves as a bridge between our customers and our development team, seeking to understand and solve the unique and complex challenges facing the energy automation sector. Last but certainly not least, we have Cedric Harrisburg, product manager of Ciprotech Digital Twin at Siemens Global. Cedric joined Siemens in 2006. He is product lifecycle manager and senior key expert for engineering tools and energy automation. He is responsible for Ciprotech Digital Twin, Ciprotech Tools, and 62050 engineering. He is also a member of TC57 Working Group 10. So now that you've met everyone, I'd like to go ahead and hand it over to Thomas to kick off the webinar. Thomas, with that, I'm going to make you presenter.
Yeah, thank you. Right. Okay, can you just confirm you see my screen?
Yep, we can see everything.
Okay, thank you. So yeah, hello from my side. Great that you join this webinar. So today we're going to speak about engineering and more specific 61850 engineering and introducing all the work that we've done on it, and we are also going to demonstrate it with real demos of real tool prototypes. So it should be a very interesting webinar for all of you. We're going to start with a short introduction of the context, who we are, why we are doing this. Then I'm going to introduce the engineering process, speak about what we understand from it, how we think everything should be done. Then I'm going to shortly introduce all the new elements that we are working on in the 61850 standard and what the opportunities of all these new developments are. And then after that, we're going to focus on the demonstration itself. So we're going to build a real system, or at least a part of it. We're going to build it together. We're going to go through each and every engineering process step and show you live in the tools how things are done. And then we're going to end with some conclusions and some next steps. Okay, so Elia is a Belgian TSO, and together with 50 Hertz in Germany, it's part of the Elia group. So 2 TSOs that together form the Elia group. When it comes to engineering, why is this topic so important for us? We are facing strong grid investments in front of us, and in order to do that and deploy digital substations, move through the digital transition, we require a very strong framework to engineer all these systems. So we are really focusing on process efficiency, life cycle management, being able to do an optimal traceability, handle changes, do a very good version management, and also interact in the most efficient way between system engineering and IED configurations. And very important as well, provide good quality of engineering at all stages of the process. Short history of the engineering topic. Already in 2012, NSOA, which is an organization grouping a lot of utilities, published a statement about engineering, about 6150 engineering, and tried to push it forward there already. And I think I can say that finally we have or we are being able to meet the statements or the requirements that they asked for in 2012. So that's very good news. Then in 2018, we worked together with some important key players of the market in a European funded project called Osmose. And that was where we funded or where we created the basics for the process in which we are right now, where we developed the ideas and took it to the next level. Then in 2020, Working Group 10 of 6150 really started developing 2 technical reports that are related to engineering, 90-30 and 76. Last year, Elia, together with 13 other utilities, published a common statement about engineering, where we try to communicate in a clear way how we want engineering to be done, and where we made recommendations to all the stakeholders in the industry, so users, tool suppliers, IED suppliers. At this stage, we are finalizing our proof of concept project. So it's a project that we started last year to develop a proof of concept that demonstrates the process. And for that, we partnered up with the people here in the webinar. So Helinks, Elvexys, Siemens, and Triangle MicroWorks. We try to partner with industry leading players to give our proof of concept project as much as possible quality and demonstration purpose. And with all of that done, we are now preparing to do the next step and prepare to tender for what we call an engineering ecosystem, where we want to go onto the market and get all the tools in order to support the process and deploy it now really within our company. That's the history. So now a few words about the common vision, the common statement that we made last year, and the process that we published there, and which is now being demonstrated today in this webinar as well. So very important is that we identify 5 different steps in the process. You could call it a top-down process, but now here on this slide, the steps are presented from left to right. So the first step in the process is called system profiling. That's a new step for 61850, and it's really a very important step where a user is able to create this concept, define his concept, by using what we call function and application templates. And these templates are being really the building blocks to build a system in all the next steps of the process. Once you combine these templates to a specification in the next step, you can then really start building a system and specifying a system or a specific IED. And with this specification then done, you can go to an IED supplier and ask him to prepare an IED configuration template based on your specification, documenting how he implemented that specification. And with these two elements available, you can then combine them in the system configuration step and really implement the system and create the final configuration to deploy that afterwards in the configuration of the IED. Within these steps, we also see opportunities to interface with other databases, with other data. For example, SIM might give us in the specification step data which we can work with within the specification. For example, a single line data for when you specify a project. And when the system configuration is done and all the engineering data is grouped in the system configuration, that data might be made available as well, again, to SIM or any other interface to be handled there as well. And very important to mention as well is that each step of the engineering process can be tested, can be validated externally with the help of testing and validation tools. Those are the main blocks of the process. What we are doing at the level of the standard is taking all these steps and making it possible to execute them. And in order to do that, two technical reports are created, 90-30 and 7.6. And the image you see here, the flow you see here, actually indicates which elements are new to the process, are new to the standard, or are being updated by these two technical reports. And in the next slides, we will take a look at each and every one of them. But as you can see already, the updates we are doing are very important, are very large to create this framework. What is very important is that all the work that we are doing is to create an efficient workflow from top to bottom, from left to right, focusing on some specific elements like device independent concepts. So being able to model a system without any device with allocation of a function. So you can really create or model a system without knowing in which device a function or an application shall be implemented. So you can really do it in a technology independent way. It's also a vendor independent specification because as we have seen, the specification will be implemented by an IED supplier within the interaction between specification and the IED template. We're focusing on process automation. If we already start from the very beginning of our process by working in an intelligent format, in the intelligent SAL format, it can allow us to win in efficiency in all the other steps and also execute some steps automatically. Change management will be much more easy to do because, as you will see in the next slides, we are investing heavily in creating unique identifiers, in creating traceability between templates and instances of these templates, between specification and configuration, etc. So all of these elements we try to put in place as well. And then the last one, but which is a very important one, especially for large utilities that have different teams working together in the same project, is that we try to create a framework that allows different teams to collaborate on the same project, collaborate on the same system, on the same SCD file. And one of the slides will go deeper into detail. So I suggest we wait for more until we get to that slide. Let's start from the left. System profiling. So we are introducing in 90-30 and 76 two new file formats, FSD, ASD. FSD meaning function specification description, and ASD the application specification description, which allows you to build a system that consists of several, or a template that consists of several functions interacting with each other, and on top of it also specifying the logical behavior of the function or a series of these functions. So an FSD is a template of a single function, and ASD is a template of a single application, combining different functions, adding logical behavior to it, adding data flow behavior to it. So you can really see the ASD more as a grouping of FSDs which interact then with each other and which get additional behavior specification on top. So as you can see here, there is no notion of a physical IED here. It's all allocation independent. It's just modeling of a system or of a specific application. Once these templates are done and you're building your system specification by combining different application templates into a system specification, then you can start building also IED specifications. And we're also introducing a new file type ISD, so IED specification description, which is now a formal way to specify an IED. And it contains, of course, the IED data model, but it also contains a process or a substation section that documents also things like behavior descriptions, might be logical as well, data flow interfaces that are expected from the IED. And it is the first step into formalizing the interaction between a user and an IED supplier, because instead of giving him a large series of written documents to specify what you want from an IED, you can give him something now that is machine readable, that is something that he can process inside his own tool, and which he can use then to create an IED capability description that takes the information from what you have given him and maps it onto his device. And that's where we come to the process ICD, which is process ICD is a new concept that we introduced in 90-30 as well, which is actually a regular ICD, which was already known, but which is now extended with the mapping information of your specification. So it contains all the necessary elements to tell a user how the IED supplier has implemented what you have specified. If the data model that you specified is conform his device, if the values that you have specified are implemented in the device, and if the data flow placeholders that you have put in your specification are being implemented inside the real device. So as you can see, this is a very efficient way of working, and this process ICD also allows you to automate the validation step on a user's side to validate what you have received from an IED supplier. And then the last one is related to collaboration. So as I said, now the purpose is that different teams working together on a project can now collaborate in a better way. Until now, we have also been being challenged with the fact that an SCD file can only be edited by one person at a time, meaning that in the different stages of your project, while the system is being handled by different persons, and when they need to do modifications, or you organize it in a way that only one person can do these modifications, or you hand over the SCD file between the hands of all these different participants, it has always been a very difficult process to manage. We are introducing what we call a system configuration collaboration file, which allows you to create from a main project a fork project, which actually extracts one or multiple IEDs from that main project and manages them in a fork project. So you can now, with this file in place, transfer the engineering rights on an IED from a main project to a fork project. You can only do it once, but when you have done it, it allows a different team as the one that is handling the main project. It allows that team to manage these IEDs in a separate environment where they can do modifications and push them back to the main project after they have done that. So it's a very interesting concept to be used, for example, to exchange information between the engineering team and the commissioning team, or within the same system, engineer different system extensions by different teams. So there are many use cases in which this concept might be used. Now, let's introduce the demonstrator, so the system that we are going to build today. Of course, we don't have the time to build a full substation, but we're going to focus actually on a single bay. And within this single bay, we're going to focus on two applications. Two applications interacting with each other. First one is the circuit breaker, and the second one is the distance protection. And of course, as you know, a distance protection trips a circuit breaker, so they will be interacting with each other. And both of these applications are being implemented by 4 devices. First one is a PIU, which holds the interface of the circuit breaker. The second one is a protection or bay controller device, which performs control over the circuit breaker, but also hosts the distance protection function. And then we have an HMI and a gateway that for the circuit breaker issue controls and manage their positions. And for the distance protection, sends or receives alarms, exchanges alarms with the bay controller or the protection device. That's the system we're going to build. A few more words about the individual applications and how we have created them. What you see here on the slide is the application template of the circuit breaker application. And within this application template, we have what we call in 90-30 4 allocation roles. First one is a PIU, then you have the bay controller, the HMI, and the gateway. And within each of these roles, we have identified the functions that are required inside that allocation role. So from top to bottom, there are, of course, inputs that wire the position of the circuit breaker, outputs that wire the trips, the open and closing commands. There are some alarms as well related to the circuit breaker that are entering the application through a wired signal. Then we have inside the bay controller the interfacing, the controlling, the interlocking, of course, and attached to that interlocking and interlocking equation. So this is an example of where we can attach the specification of a logical behavior to a function. And then, of course, the alarms are being sent to the HMI, to the gateway, and also the controlling can be done from those two places. This application is a container on itself, but it also interacts with other functions from other applications. For example, for the interlocking, it receives some some information from the high voltage switches from the bay. There is additional interfacing with the control center, with the HMI screens now. And on the other side, exactly the same. The alarms are being sent to the functions inside the applications of the HMI and the control center. You can do the same exercise for the distance protection. The distance protection, is an application from another. It's a completely different type. It also has a binary input. In our case, it's just an example here, to switch between the overreach and the underreach setting. There are some protection functions. There is a trip logic, which we have modeled in 61131, which really documents how the trips are being created from the operations of the different distance protection zones. We have a logic that does some things, which has attached to that function a specific 61131 logic. We have LEDs that are being activated. We have, of course, the tripping itself. And we have data flow with other functions. Again, same thing like in the circuit breaker. There's again interfaces on the left and on the right. Of course, the distance protection needs currents and voltages, needs input from the teleprotection application. The auto recloser, of course, is interacting. And so you see again, this application, it's a container on its own, but it interacts also with other applications. All these interactions, we can already model them inside the application template by placing what we call process resources, by placing placeholders in the application template itself to start creating the data flow once they get instantiated in the same system where these other functions are available. Coming back to the big blue box in the middle, the 61131 trip logic, just to show you what is behind it. So this is a logic that comes from the concept that we have within Elia, and that allows us now to document in the 61131 language how all the signals need to be treated and how the trips and other signals are being created from it. So this is really now an added value enabled by the behavior descriptions that can now be added to the or attached to the applications. When we have the circuit breaker application template, the distance protection application template, when we bring both of them now together in a system, these applications can interact with each other. Of course, the trip is going from the right to the left, from the tripping function from the distance protection to the circuit breaker interface. That is use the trip and that forwards it to the binary outputs. And we also have the circuit breaker control function providing a signal to the logic inside the distance protection function. I think that's the signal that activates the switch onto fault zones, for example. And once these two applications are being put together, then they can be implemented into the different devices. So the system that we will be building will consist of the 4 IEDs in which these applications are being implemented, and between which now exists data flow in the type of wired internal data flow as well, reporting goose or MMS control. So that's the demonstrator. That's the system that we're going to build today. The process that we will be demonstrating is exactly the same as the one I explained in the slides before. By taking from the profile side, from the top of the process, taking both application templates, building inside the Helinks tools a system specification from it, building the individual IED specifications, then handing them over to Siemens in order to create the ICD files, and then afterwards combining both of them inside a system configuration, which can then be used to finalize the configuration of the IED. And Triangle will demonstrate how an individual application can be simulated and tested so that it can be validated and used inside the remaining steps of the process. And now we're going to hand over the screen to Yannick. But if you can do that.
All right, thank you, Thomas. Yannick, I'm going to go ahead and make you presenter. You should now have the screen.
Okay.
We're not quite seeing your screen yet.
Okay.
Oh, there we go.
Yes, now you see my screen and you can hear me.
Yes.
Nice. Okay, let's talk about the profiling part and demonstrate the use case of the specification of an application The profiling part is the first part introduced before by Thomas. Okay. The technical reports 90-30 and 7-6 extend the SCL data model, or more specifically, the process section of the SCL data model with additional elements. This element allows the specification of the IEC 61A50 system in an ID manufacturer independent way. The current slide shows how some of these elements are represented in Helinks STS. On the left part here, you can see the bed template. And on the right part, the function diagram gives a static view of the function. Here, for example, the logical node, the data attributes, the allocation role, and the behavior descriptor. The function can be allocated either on bay level, like this here, or on equipment level related to an equipment of the bed template. The allocation role allows to group function and assign ID role to it, and this grouping does not yet require a manufacturer-specific physical ID. It means we can really do this in the top-down approach without the knowledge of the manufacturer ID. The behavior descriptor are the elements that contain the logic definition. Thomas has just introduced this just before. With you can define this logic with a textual descriptor, but you can also define this logic and express it in 61131. The data exchange is an important part of the specification and can be also done in physical ID agnostic way. The content of an application can be stored with the new standardized file, the ASD file, the application specification description file, as described by Thomas just before. And in this slide, you see how it's reflected in Helinks STS. And you can see here the application is really defined with exchange between functions. And this exchange use some specified services. And that means during the specification, you can already decide or specify what kind of service you will use to make a data exchange. Here you can see some GUI message. You can also see reporting. But now with the 90-30 extension, you can also specify internal connection inside the same ID or a wiring connection. And at this place, when you define the application, and as Thomas explained just before, you can already define process resource, which is the pink element here. And this process resource acts as placeholder for function not yet available in the context of this application. For example, this is the application of the circuit breaker, and you expect signal from the switches, from the disconnector switches, and these are not part of the application, and it's represented with process resource here. Later in this demo, we will show you how these process resources are resolved when we combine multiple applications inside the project. And this slide shows you the step to define an application. First, you design the function as well as the signal and the inputs necessary for this application. The signal are the output signal and the input are the input signal, basically. You can add behavior descriptor as expressed before. to describe in textual format, but also in 61131, the complete internal behavior of your application. You use the drawing feature of Helinks STS, as shown here, to describe this exchange based on services. And then you can export this application to an ASD file, and this ASD file can be used to create your the specification of your substation. It can also be used to exchange with other tools in a SCL standardized format. Now I will show you this in the tools directly. I have two projects here. The first one is the profiling project. And in this profiling project, in the single line drawing, I have defined a template substation with a template voltage level and template bay. And in this bay, we have, several functions defined, and also the signal for each logical node, the output signal are also predefined here, and also the input signal. And this output signal and input signal are also represented in the extension of the 90-13 with DOS and DAS, and the inputs are defined with source ref elements. I will show you also in this profiling project the application. We have the CB application, which is described in the PowerPoint, but now we have also the P21 application, the distance protection application. And you can see here this application is a little bit more complex. We have a lot of internal connection inside the protection between several sub-functions. And we have a lot of pink function, which is the process resource, which represent the process resource. And for example, here you can see that the trip main protection signal will be sent to this process resource to the circuit breaker. And this process resource will be later in the project resolved and replaced by a function of the circuit breaker application. And we have another process resource on the bottom, which gives the operation close.general signal, which is sending this case by the PIU, which handle the breaker to the protection ID. And as soon as you have defined the exchange like this, you can then export the file. And to export the file, you just right-click on the application itself and use the export button. And this will generate on the output folder a file. Correct one, yes, it's the correct one. We'll generate a file. I will just quickly show you what is inside this file. It's an SCL file, a normal SCL file, but with the adding of the 6-100, which is the namespace for the 90-30 and 7-6 technical report, where you have all the process resource, you have the application, and all this kind of things. You have the behavior descriptor. Here you have all the logical node of the specification with source ref, DOS, DAS, and everything coming from the 90-30 is now part of this file, which is now exchangeable between other tools. Then if I come back to the PowerPoint, okay, we have now passed through the first step, the profiling phase. We have specified application. In this case, we have specified the CB application and the P21 application. And we have stored this application on ASD file, or as it is the case in Helinks STS right now, we have stored this application in the internal library. We have also probably stored in the SSD file or inside the internal library some bay template. Then we are ready to move to the second step, the specification of your substation based on this file. And when we have done this step, the substation specification, we can then export some specification file. We can export the ISD file, which is the ID specification description file, and which can be used later by the manufacturer tools, the ICT tools of the manufacturer. We can also export SSD file, which represents the complete substation, and this file can be exchanged in our demonstrator today with Triangle for the testing tools. And we can also export an SSD file for the demos for the system configuration tools, which in our case is also Helinks STS. Then this file will just show you what I have already explained just before on the P21 application. We have some process resource that represent the sending of the trip signal to the PIU, which is on the profiling phase represented with a process resource. And in the project, as soon as we have instantiate the two applications together, we will resolve the process resource. And by the resolving of the process resource, this signal will now go to the function of the PIU, which will handle the trip. On this slide, you see also on this step, the specification step, we will generate the ISD file for the manufacturer, and these are the steps required to generate this file. First, we need to define the allocation of each function, then with the allocation role. Then we need to generate to craft the specification ID, and this will generate the data model of the specification. And then we can later export the ISD file. At this stage, we can also export the SSD file for the testing tools. Now I will show you this. Oops, I will show you this in the project. I have the second project, which is the specification project. In this project, it's no more template, but it's the real substation that I would like to specify. In this case, it's the Bruxelles substation with only one bay. And in this project, I have instantiated my two ASD files, the CB application and the P21 application. And I can show you in the P21 application that now these two process resources now resolved and implemented with a function coming from the CB, the PIU for the CB application. And also the closing of the breaker is also resolved here in this project. And then if we come back to the single line, we can then create the data model of the specification ID. Yeah, I will just create like this. And I will create the same for the protection. And then if I show you the system diagram here, we have now two specification ID, one for the PIU and one for the protection. And we can then export the specification that will be shared with Siemens. Here I export an ISD file, and I export also the ISD file for the protection. And this will generate these two files here. And if I quickly show you what is inside the file, as Thomas said just before, it's really an ISD file. And in the ISD file, you have the substation section where you have all the information coming from the 90-30 technical report with all the source ref, all the DOS and DAS that are used for the specification of this ID. Then you can give this file to the ID manufacturer, and we will come back with a process ICD file that resolves your specification. At this stage, you can also export a system specification file. Of course, if you export a system specification file, you need to have the substation section, because every extension of the 90-30 is inside the substation section. And also now in this file, you have the substation section with all the information of the 90-30 and 7-6 that will be used by Triangle in the rest of this demonstrator to demonstrate the testing part. Then I think I need to pass the end to Jackson.
Okay, thanks, Yannick. Jackson, I'll go ahead and make you presenter.
All right.
And you should have the screen.
Okay. All right. Thank you, Yannick, and thank you, Beth. As mentioned, my name is Jackson Moore, application engineer here with Triangle MicroWorks, and today I'll be introducing step 3 in this top-down specification process, which is system simulation and engineering validation, shown here highlighted in blue. Now, the goal of this step is to take the design that has been specified and to make sure that it actually works as intended. So this can be an iterative process. By that I mean that the testing can occur as the design is still being developed, for example, in Helinks, as Yannick showed us, or it can be done once your design is complete. So that would be you've produced both your ASDs and your SSD. But what's really unique here is how early on in the design process we're able to perform the simulation and validation. In this case, before we've even chosen the IEDs, meaning that any errors that have been identified at the stage are comparatively much cheaper and easier to fix than they would be down the line. So as part of this step, we see several lines representing different SCL files that are flowing into this yellow box here at the bottom. This yellow box represents the simulation and validation tool, which I'll be demonstrating in a moment using DTM. So there are two types of files that are coming into this simulation and testing box, and those are going to be ASDs and SSDs, which we've been speaking a lot about. Yannick just explained those as well as Thomas in detail a few moments ago. So the CB ASD over here on the left, this would represent a circuit breaker application, whereas the P21, P standing for protection and 21 being the ANSI code for distance protection, would specify a distance protection application. So the other file that could be passed in would be this SSD down here. As we said moments ago, SSD can instantiate these ASDs that we've already created, assign roles, and allow you to specify an entire bay or an entire system, which can now be simulated at this specification stage. So today I'll actually be simulating and validating the P21 ASD. And in order to do this, the first step I'm going to need to do will be importing. So what you see up on my screen now is actually a screenshot of the import dialog box that we'll be looking at in just a few moments. And I'll use it to import the distance protection application specification. And what I really want to drive home here on the screen is that I am beginning with an SCL file that was produced as a part of this specification process. And then all of the visualization, simulation, and testing that I'll be doing afterwards is all coming from this one file. So you'll notice that there's different sections of this import dialog box, and that these roughly correspond to what you might see if you were to open up a typical SCL file. So up here at the top, we have the communication section, below that, the substation section, and then the IED section down here below. Now in ASD, the one that we're going to be working with today will only contain the substation section. So that's really the only one that's going to be relevant. But as I mentioned, this is really applicable to both SSDs and SCDs assuming that these were produced with the top-down engineering process that we're talking about today. Everything else would apply to those as well. So once I bring in that ASD file, I'll be able to visualize what's inside of it. I really think of ASDs as kind of containing two crucial parts. The first being a description of the data flow, and the second one being a description of the behavior of that application. And what we see here is a visualization of that first part, the data flow. So for the distance protection application specifically, that's what we're looking at. We'll see the inputs over here on the left. This is what we refer to as process resources. Same thing over here on the right. These are outputs. Inputs are flowing into functions, and within that sub-functions, and finally LNs down at the bottom. And then we also have this P21 here in the middle. This is going to be our behavior description. And this is described in IEC 61131. So if you're not familiar, IEC 61131 it's really a family of programming languages that's popular in the control and automation industry. Variants of it are ubiquitous in programmable logic controllers, or PLC. So as part of the specification process, a utility may describe the desired behavior of a specific application using this language. And this really serves to both remove ambiguity from the purchasing process, but also it's got the also the benefit of allowing for enhanced levels of validation and simulation, which is what we'll be looking at in just a moment. So if we kind of zoom in and look at what's inside of that that box there labeled P21, this is a peek inside the IEC 61131 logic. So we can see that this is written using the function block diagram variant of 61131. So this is going to be a graphical programming language that closely resembles the logic diagrams that paper specifications have been based off for some time. So much like the application visualization that we looked at a moment ago, the inputs are coming into the left and the outputs are coming out on the right. But instead of flowing through somewhat ambiguous functions like we saw at the application level, here it's very specific elementary operators like ands and ors. So we really, have a very clear picture of how our logic is operating, and we can actually simulate it and run it. In order to do that, there's a couple different ways that we can interact with our application. So the most basic method would really just be to come in here and manipulate a specific input, and then we'll be able to watch outputs as they're updated. We can manipulate multiple inputs simultaneously and make sure that our outputs all update as expected. Now, if I do want to update, let's say multiple inputs, and I know that for this given combination of inputs, I should have a predefined set of outputs, we do have a integrated test sequencer that allows for that. So basically one row in this test sequencer would have a predefined value for every input that's flowing into my application and an expected value for every output. And in that way, we can validate and make sure that our application that we've designed actually works as we expect and as we intend. All right, now I'm going to pivot over to actually seeing the application so we can see it in action now that I've kind of given you that background and description. So what you see up on my screen now is I guess a pre-release version of the tool that's not yet available, but this is what we're using to do the design and the demo today. It's DTM, or Distributed Test Manager. So the first thing I do, as I mentioned before, is actually import that ASD. So I come up here, go to the import substation wizard, and I will select that ASD file, that application specification description that was produced as part of the specification process. As I mentioned, the only section that'll be relevant for me is going to be the substation section, because that's where all the information is contained. I would want to make sure that I check the box to allow 6-100 elements. Because those are going to be crucial in order for the simulation to operate and those data flows to be defined. From there, once I import the ASD, I'm going to see this reflection over here on the left-hand side in the workspace tree that corresponds to the substation section. So up here at the top, I would have a a substation, in this case just called template, voltage level, and then a bay. And then within that, I'll see the different functions, which may correspond to FSDs or functional specification descriptions that were combined into the ASD. So if you were to open up the actual STL file, the XML, you would see a hierarchy that looks quite similar to this. This is really a direct reflection of the STL, and then I think it would be fair to say that this diagram that we see here is a direct reflection of this tree over here. So for example, the teleprotect function that we see here, if we expand it out, we see several sub-functions within it. And then within those sub-functions, we see LNs. If I come over here to the teleprotect function within my application visualizer, I can expand out the function, and within it, I can see the sub-functions, and then finally the LNs within that. I can see how my process resources or inputs are being passed into those functions and outputs are coming out, and in this case, being passed up into our P21 XML. So as I said before during the slides, this right here is actually the behavior description. So included in the ASD file that I imported was a reference to this 61131 file. So it's like a local file path. When I import the file, I go and look for that 61131 file and bring it in. Taking a peek inside of that 61131 file, here's that function block diagram that I described before. So this is something that describes really the exact behavior for a specific distance protection algorithm. As I said before, it's made up of really inputs, outputs, and what I call elementary operators, but ands, ors, timer on delays. If you're familiar with PLC logic or controls and automation programming, hopefully it should look pretty familiar. Now I can interact with this in several ways. As I said, I could come down here at the really at the IEC 61131 level and begin to manipulate these inputs and outputs. I could edit my logic if I needed to and test and validate here, or I can do this back up one level at the application level. So here, because inputs are flowing into that 61131, I simply have to manipulate one of these process resources or inputs on the left-hand side, and I'll be able to see how my application actually works. So go ahead and just set true for one of these distance protection operate signals. And when I hit apply, we'll see some red flash up on the screen as that signal changes to true, flows through a couple functions, ultimately into my behavior description, and activates several outputs over here on the right. That is reflected, of course, in the output tree over here as well. Now, if I, am worried that it was too fast and I missed it, I can click on one of the values. So for example, this true, and I can see that some true to false toggles have happened as I've been playing around with this project throughout the day and have the exact timestamps. I can also set up a capture and playback. And again, if tight timings are an important part of my application working correctly, then I can capture that and play it back to see what happened. Now, because it can become tedious to test complex schemes repeatedly, especially as I'm making changes, there's also the opportunity to use the test sequencer. So the test sequencer really does kind of a similar thing to what I did here, where I selected a specific input, set a value for that, but instead it defines inputs for, or values, I should say, for every one of these inputs and expected values for every one of these outputs. Effectively, it sets the values for these inputs, waits a short period of time, and then monitors to make sure that these outputs are correctly set. And it's done using a table interface. You can define these tests using Excel, allowing you to rapidly scale up and perform many tests very quickly. You can, of course, use other scripting methods to define more complicated tests, and in the near future, you'll be able to do that using a graphical method as well. So with that, I hope I've demonstrated how we've been able to both validate and test and simulate our applications. As I mentioned, this could also apply to our SD as well. And then later on in the engineering process, once we complete specification, our SCD.
Okay, thanks, Jackson. And with that, I believe we're handing it back over to Yannick.
No,
the next one
to
is Cedric.
yeah.
I'm sorry, to who?
Me, to Cedric.
To Cedric.
Oh, Cedric, sorry. All right, Cedric, you should have this. There you go. We can see your screen.
Okay, great. So now let's go to the fourth step of the process introduced by Thomas. We had before the IEC specification file generated by Yannick. And with the Siemens tools, I will show you how to generate the ICD file and the so-called process ICD file that has been introduced as part of that project. So the workflow that I will show is how to read the specification file for both devices, the protection device as well as the merging unit, to map it to the signals provided by default by the manufacturer product, and how to deliver the process ICD file. The process ICD file will have the particularity of including the specific mapping as well as the deviations, if any deviations are found in the product, that some logical nodes or some names cannot be realized in the vendor tool. To show that, I will jump then to the Dixie software. The Dixie software is our IED configuration tool used to configure all CProtect 5 devices. So in that case, our 6MU device merging it, as well as the 7SA87, which is the distance protection device commonly used at Elia. Those are standard device configurations here as they exist in our library without any specific features or any specific customer configurations yet. So why we have selected those devices is because the 6MU device type is the best fit for merging unit application, and the 7SA87 also one of the best fit for supporting distance protection function, which is used in the prototype demo. So the Dixie software is providing multiple functionalities to support the engineering of top-down engineering with typicals. Today we will focus on the one using 16Y50. So as mentioned earlier, every device from the manufacturer is coming with its default data model. Why? Because the 16Y50 standard is standardizing logical nodes, but it's not standardizing the structure with logical devices or the prefix and suffix names used in the protection functions. So here you see for a distance protection device from the Siemens CProtect 5 family, by default it is modeled with a logical device called LN1 distance prot and containing a certain number of zones by default. Now we will see in the specification generated earlier how to map the expected data model with the one provided by the specification. So for that, we just need to import first that new format introduced here's the ISD specification. We have both for the merging unit and for the protection device. Let's start with the merging unit. The merging unit that is expected to be delivered at the end of the engineering process is containing those logical devices, the CB interface, the CT interface, DT interface, and so on. And we'll do the engineering starting from the substation section. So for that, let's go to the circuit breaker structure, where we find the most important functionality of the merging unit here, being the position of the circuit breaker. You get a device called template in the specification. You just map it to the device from the Siemens library. And by default, some magic is happening that is recognizing that our default device is having also an XCBR but not in a logical device called CB interface as required by specification, but in the logical device called CB1. It is finding it. If it wouldn't find it, we have the possibility to select other logical devices that better match the specification. But here, this is a perfect fit. And you see that the majority of the required data objects are already provided in the device. Some are not there yet. This is especially the case for signals that will be received via GUIs from the protection device. So for that, we have the possibility to create external signals coming via GUIs by creating them with that blue icon. The signal is now created and the match is found. I iterate the same for the other signal, and at the end, we end up with the required GUIs inputs for the device. And in case of a data object required but not modeled that way by default in the device, we have the possibility to select a better match in our device to meet the specification. Doing that, every signal from the specification is mapped one by one between specification and the default data model of the device. This process has to be repeated for every application. So if it's the implication of the CT interface, now it's about finding where the CCTR applications are located. And we iterate that process for every element, the CT, the VT, as well as the other signals available in the device, such as the time synchronization signal also required in the application and now matched by the device. Once that mapping is done for every signal, so either the signal exists by default and it's just one-to-one mapping, or it's about creating the required functionalities and signals into the device, we can export that process ICD file with a new option containing now the process ICDs that will inform what are the data supported by the device. How was the original name in our tool by default, and how is the signal in the specification. So we can do it that way to keep exactly the same names in our device by default, or if the purpose from the utility is to go towards a unified data model and more interchangeability, have no deviations at all, we have then the possibility to import the data model changes into the device to take over all the logical devices, logical node prefixes and suffixes into our data model. This is what I will do now to import data model, and we will see that now that merging unit and device is containing exactly the name as required. The circuit breaker is called CBXCBR1. The LTMS one was called LTMS0 by default, has been changed, and therefore reducing or avoiding as much as possible the deviations between the specified data model. So now that the device is exactly or as close as possible from the specification, I export again the ICD file as process ICD, and I hand that over to the next step of the application. The same process can be repeated then for the protection device. For the protection device, I just select the protection ICD file, and for the protection ICD file, same procedure. I have there a distance protection function with a first zone. I select the device where that functionality is realized, and that functionality is realized as stated in the distance protection function. I map all the signals the same way, adapt the data model again, and export the process ICD file so that I can hand over to Yannick for the next step of the presentation.
Okay, thanks, Cedric. Yannick, I'm going to go ahead and make you presenter. Okay, you should have the screen.
Yes. Can you see my screen?
Yes.
Okay. Let's move on the next step and the final step for me today, where we receive the feedback file from the ID manufacturer, the process ICD file just mentioned by Cedric. We will use the process ICD file provided by all the manufacturer in the substation and all the 90-30 information contained on it to implement our specification. Finally, we will be able to generate an SCD file which contains the complete substation configuration, the control block, the dataset, the XREF, and all this that fit our specification and the ID manufacturer ID. This file can then be exported again to the manufacturer to be loaded in the ID itself. These are the slides show you just the process of the importation of the process ICD file. I will demonstrate this in the tools in a couple of minutes, but basically you import the process ICD file from the manufacturer. You create an instance of this ID because it's the process ICD. It's still a template. Then you need to create an instance. You use this instance in the allocation role. You implement one allocation role with the instance, and then the system automatize for you the implementation of the logical node based on the information stored in the process ICD file. And this information is stored in the process ICD file with all the steps that was done just before by Cedric. And the system will also automatize the usage of the letter binding because the information of the letter binding that was demonstrated just before also by Cedric is also stored on the process ICD file. Then we can automatically implement the source ref element, which was the specification inputs that we create just in the substation specification part, the previous part. And the system gives you also information if, in this case, it's no more the case with the latest file, but in one file we have one signal which was not mapped in the process ICD, and then the system gives you also information that this signal is, for example, missing in the process ICD. Then you have some feedback. As soon as you have implement everything, that means all the L node is implemented with logical node from ID, all the DOS, the data object specification and data attribute specification are implemented. Every input, every source ref is resolved with XREF of the ID. All the process resource is resolved. You can then generate the communication that will build and or configure dataset and control block, and then we'll create XREF or complete pre-existing XREF in the ID. And you see here in the dialog, and we will see this later in the demo, that we provide a complete log dialog, which allow you to understand what's happening. Here it's all the step, but I will show you all this step in few minutes. Finally, you can then export the SCD file for the manufacturer. Then I will go on the demo. We have still the same project, the project we use to export the ISD file. The first step is to import the process ICD file. Then I go on the import button here, and I have received my two process ICD from Siemens. One is for the merging unit for the PIU, and one is for the protection. I will import the merging unit. Okay, and I will import the second one, sorry, the protection. Okay, then as soon as I have imported these two files, if I go on the system diagram here, oops, sorry, I need to restart the system diagram. I think it was already open. Demo effect. Here on the palette, you see the both process ICD file, one for the merging unit and one for the protection. I can then create instance of this template. I will name it, this one is the merging unit. I will name it Siemens PIU. And I will create an instance of the protection. And I will name it Siemens protection. I would then just connect this two ID to the subnet, just to make it proper. Oops, sorry. Okay. Then if I come back to my bay, it's currently implemented with my specification ID. I will virtualize everything. It's no more virtual. And I will implement the PIU in this bay with the Siemens PIU. And I will implement the protection with the Siemens protection. And when I implement my specification with a process ICD file, with an ID generated by a process ICD file, the tools will read the information, the 19-30 and 7-6, 6-100 namespace information inside the process ICD file, and will automatically, you see, I don't know if you see on the screen, but on each logical node here, we have, if we are on the virtual step, we have an open icon, and when we are implemented, we have now a close icon. That means this logical node is now implemented, and it's implemented with the information given by the process ICD file, given by the job done by Cedric just before. Then I can also show you, for example, in the PIU here, you see all the structure defined in the specification and the structure where it is implemented. And if I see you this example here, for example, we have all the logical node in the PIU global is implemented within a logical device PIU global in this ID, except that this one, because probably in this process ICD file, the step done by Cedric just before, where it's defined the same logical device structure, was not done for this one. Then you can quickly also see if your specification and your implementation is fitting one-to-one. As I said before, we have for example, on the XCBR here, we have some input predefined. And here, for example, two of these inputs, the close and operation open and operation close, are resolved with real xref in the ID. This was done by Cedric just before. It has created some xref for these two specification input to source ref. And we can see here that these both xref are now correctly implemented. These both source ref, are now correctly implemented with xref from the ID. There was some other one maybe created just after the exchange of the file, which are still open. Then when we have do all this job, we can then generate the communication. Just before generate the communication, I will show you the communication editor, where you will see, okay, we have two ID, the Siemens PIU and protection, but we have no data set in this ID. If I show you the matrix of goose, we have no goose message, and we have no subscription to goose. And if I go also in the input representation of our SCD file, for example, in the PIU, we have 28 X12 predefined, but this subscription is not currently connected to a publisher goose control block. Then I will generate the communication based on the information in our specification, all the exchange that we have defined in the application. We will generate a communication. That means we will generate the data set, the control block, and generate or use the X12. I will click on process here, and we will see a complete log. Here you see a red cross. Red cross is not something that doesn't work. It's maybe there is some error, and we will go inside the error and see why there is some error. Here you can quickly see that there is some function in our specification which is used in the communication, but it is currently not assigned to a device. And currently all these functions are the process resource, which are not fully resolved in our example, because in our example we have instantiated only the P21 application and the CB application, but for example, we don't have instantiate the VT application and the CT application. And of course, the P21 application is pending on some CT and VT signal, which are not yet resolved, and that is the reason why we have this error. But if I show you, the result, for example, for the Siemens PIU, we publish some goals. If I go a little bit down in this dialog, you will see we have some application. We have the CB application, which extends some goals from the Siemens PIU. And in this application, we will exchange the position of the breaker, for example. And we will implement this. And to implement this, we have created a control block, the GCB F1. And in the GCB F1, we inside the dataset, we have generated the dataset in the SCD file, and inside the dataset, we have put the position, and we have prepared the subscription in the protection ID. And for the Siemens PIU, we also subscribe to some goals. And for example, here you see that we reuse two existing X12, the operation close and the operation open, which was information in the process ICD file that we have used. And for some other one, we just create the X12 because the X12 was not predefined in the process ICD. And then if I show you now the communication editor again, and if we go on the dataset, then you see that for the Siemens PIU, we have now some goose control block created with the position of the breaker, and on the protection, you have some other goose control block with some signal, for example, the trip, which is coming for the P21 application and which go to the PIU. If I show you the goose matrix, now we have some goose messages which are published and subscribed by the other ID. You can see this with the yes here. And if we go on the inputs side for the PIU, just before we have 28, but now we have two other X12 defined for this ID because it was not predefined in the process ICD, and we have reused the X12 for the op close here and the X12 for the op open. Here you see there is an error. Probably I have made a mistake somewhere, but that's it. And then we can export. Finally, we can export the SCD file to export the SCD file, you use the SCD file. Here you can select the edition 1 to 2.1. In this case, we will use 2.1. And we can then export the SCD file, and the SCD file is now available on the bottom here and can be sent to Siemens in this case for the next step. And that's it.
Okay, thanks, Yannick. And I believe I switched back to Cedric.
All right.
Make you presenter, and you should have the screen.
So now let's come to the last part of the presentation, what to do with that SCD file containing the data flow of the signals. So this is something that is common on the market. It's nothing new in that project. That IEC configuration tools can import SCD files from different system configurations tools. As Siemens, we're having our own system configuration tool, but we can also import SCD files coming from the tool from Yannick. So I will show how to import that SCD file and then generate the configuration and give you a sneak preview of testing possibilities of that configuration. Either in a real device or today in a virtual device that is easy to show in such a virtual meeting using our simplex digital twin. So for that, let's go to again our DXC5 software. Remember earlier where we were importing those ISD file to generate the device configuration. Remember that we were having options to import the data model, and earlier I imported only the logical device, logical node data object structure. Now it is about importing the communication flow, the report, the goods and sample values, or if it would be used, it could also import the protection parameters model TS1650. So we can do either the import via that menu or using our 1650 station, selecting the file to be imported and select the file provided earlier by Yannick. I've already imported it earlier, so if I show that into our own system configuration tool, you can see that, for example, the GUIS configuration has been imported. What is sent from the PIU, so the merging unit device, to the protection device, or what the protection device is sending back to the merging unit. So the import of SCD is just a single click. The validation can be done in our own system configuration tool, or can be done then with a real device or with a virtual copy of the device. This is what I will show you now. So for that, when the configuration, the engineering is finished, to go to the simulation step, we can export individual devices or multiple devices in a so-called simulation format. And the simulation format is then something that we can simulate into our simplex digital twin, where every simplex 5 device, no matter if it's merging unit, protection device, distance protection, or any other overcurrent protection, can be simulated. And here I'm simulating currently 2 devices. Our merging units we've been talking about at the beginning, and the protection device. Both devices are running at the same time. And if I inject voltages and currents at the merging unit that are then transmitted via sample values to the protection device, you see that the values are received at the protection device. Here, this is the front display of our 7SA87, where we have the navigation possibilities that you know from the real device. And to validate that the values are transmitted, I can see in the display, if I increase the secondary values for the current, it's reflected, the primary values are getting higher. And as some overcurrent protection has been configured, here it is showing, for example, that the sample values are transmitted and the threshold used for the overcurrent protection is correct. And that way, I can test various protection applications. We have also the possibility to connect to that environment, to connect via a 1650 client to verify the data model. And here to see, for example, that the model of the CT inputs with the required name, phase 8, CCTR 1, 2, 3, or the neutral has been taken over into the device, or the name of the circuit breaker that was required to be CDX CDR1 is available in the environment, currently simulated with a position 10. If I just simulate now a position open for the circuit breaker, it's switching from 10 to 01. So that way can validate the data model implemented in the device. We can validate the data generated by the device and the communication possibilities of transmitting data between emerging units through a protection device. And with that, I'd like to hand over to Thomas to conclude the webinar and go to the Q&A.
Okay, thanks, Cedric. Thomas, I'll go ahead and make you presenter again to wrap it up.
Yeah. Okay, so first of all, thank you to all the other presenters for giving a very clear presentation of the process and demonstrating many of the benefits that we can easily identify. I'm going to conclude with some of the most important ones. So first of all, user concept and the specification is now from the beginning of the process translated in a machine-readable format. We can specify many things, so data flow values, logical behavior specification, independent from the implementation afterwards. All of that can be simulated and tested before it gets implemented. So this is one of the very big advantages, is that you can now test what you have engineered before it gets implemented in a device. So many of potential errors can now be identified much earlier in the engineering process. And also with all of these data in place in SAL, we can think about opportunities for creating automatically the documentation of the system based on that data, and not necessarily in diagrams, but more in a dynamic way where somebody can browse through the system based on all the SAL data that is available. As we have seen, the interaction with the IED configuration tool is being standardized, is being optimized, which results in less interpretation errors, because the IED supplier does not need to dig anymore into many documents which a user provides him. He gets a machine-readable file which he can automatically interpret in his tools and document what he thinks his device needs to do in the same way, in the same type of file. So there's more automation in the overall interaction, more quality, and also an improved interchangeability. So when a user builds an ISD file, he does not build it specifically for a specific IED supplier. In general, it should be a generic IED specification, which a user can then give to multiple IED suppliers and see from their responses what is the best quality offer for them. The system configuration, now if many of the engineering steps are being enhanced and additional effort is being put in place in the earlier steps, of course the system configuration step can profit from that and more automatically create the system configuration. And then, yeah, if we compare what we consider now as a top-down engineering process with a classical bottom-up process where you start from the capabilities of the IED and build your system with that with taking that into account, we believe that there is a much higher process efficiency here and an improved engineering lifecycle management possible, because your concept from the beginning again is already machine processable, contains the necessary identifiers which you can trace down up to the system configuration. Now, what are the next steps? So we're almost ready with 90-30 and 7.6. I've seen some of the questions also asking when these documents are becoming available. So currently they are in the draft stage. They have been circulating inside working group 10, and now we're really in the very final stage of before sending out the DTR. So probably somewhere, I would say, beginning of 2024, things will be circulating, and then it's in the process of publication. So somewhere I would say mid 2024 by the latest, these technical reports will be published. They will also include SAL examples. So there will be SAL files attached to it. There will be the new namespace extension. So everything should be there. We try to explain things as good as possible. So that's for 2024. We also, within Elia now, will be starting a software project to take the next step to get the tools for a final solution in order to be ready to do first projects in 2029, 2030. But first of all, we plan to start developing in 2025 in order to start developing our profile in 2026. Probably we will continue to do some piloting, some improvements, just to get things ready. But that's more or less the time frame we are looking at. So 2024 start, 2026 starting to create function application templates, creating typicals, IED specifications, and then so we are ready for 2027 when we are going onto the market to purchase devices. And then normally around 2029, 2030, our first project should be starting. That's it. I want to thank you all for listening. If there is some time, if you still have some time, we can take a couple of minutes to address some of the most important questions. And also thank you to Christoph and Andreas for answering. I see we have a lot of questions, so that's very good. I'm very happy with that. Let's take some of the ones that you have given a star, so we can take a look at the most important ones. So yes, 90-30 7.6 will be coming out as soon as possible. So I would say by the latest mid 2024 they shall be published. Yeah, that's another one related to the publication. Yeah, so indeed the signals, specifying the service of the signal. Indeed, when you are specifying data flow, you have the opportunity to specify the service of that data flow, but it's an optional thing. If you don't know yet where it shall be implemented in, if the sender and the receiver shall be implemented in the same device or not, you're not forced to specify the service. You can still keep things open. And inside 90-30, we give some recommendations on how to handle how to handle the service when functions are being implemented by the same or by different devices based on the service that was specified. So that's a thing that should be covered. Then Yeah. So of course we are bringing this forward to working group 10. It was actually the biggest purpose of our strategy was not to specify something or create something and then push it to the standard. No, the goal was to develop together with the standard, first the standard and then the solutions. And I think we are doing that. Okay, IED name is template in SL. Yeah, indeed. So if your template, if your SAL file is a template, ICD or ISD, ISD in the case it is a template of an IED specification, ICD if it's a template of an IED capability description, then the rule is to name the IED template in SAL. Then here a question about the ISDs, indeed. Yeah, so the definition of the ISD is that it specifies a specific IED configuration with a specific IED data model. And of course, you can create as many ISD files as IEDs that you need, but while you specify it as a template, the idea is to reuse it in projects and instantiate it in projects there. So the goal is not to do for every project the same process, but to specify your IEDs in the beginning or in the asynchronous stage of the engineering, where you create a library of ICDs, which you can then instantiate into different projects. What we do at Elia as well is create what we call cluster IED configurations. And a cluster means that it is an IED configuration which you can use for several type of implementations, for several type of BAE typicals, or several type of, depending on the context of the implementation. So there are many strategies to tackle this problem and limiting the amount of ISDs you need to manage and the amount of interfacing with the IED supplier. Okay, so this is about the mapping of every. I think the answer I just gave on the previous question, it applies here as well. Okay. Yeah, and I think that's here replacing an existing IED vendor with a different one. I think that's one of the biggest purposes of this process, is that these kind of things become more easy. And as I said, an ISD is vendor independent, and you can easily give it to multiple IED suppliers and get multiple offers back. And by documenting the mapping of your specification onto the device, it makes it then in the system configuration more easy to replace an existing device with a new one, because it's based on the same ISD file originally, and because of the mapping information, because you give already in the ICD file the information to the system configuration tool how we need to implement that device onto the system. So it's something that should become more easy now with this process in place and with the new enhancements of the standard. Yes, the webinar is going to be available. All participants will receive a download link, if I'm not mistaken. But perhaps you can elaborate on that.
Yes, so everyone that attended today will receive a follow-up email with a link to the recording. Also, once you leave the webinar, you will be presented with a survey. We really appreciate if you took about 2 minutes, 3 minutes to answer that survey and give us your feedback. And that will also include a link to the download as well.
Okay, thank you, Beth. Yeah, so as Beth said, yeah, you will receive a survey. We will ask just a very few questions because we want to get a little bit of ideas of how interested people are in this process, how happy they are with what they have seen, and how they think this will move forward inside your own organization. So please help us with that, and please fill in the survey. And in general, I would like to thank you all. I think we are done. Beth, do you want to say something?
I think we're ready to wrap up. I think we've addressed all the questions. And again, thanks everyone for attending today.
Yeah,
okay.
Thank you, and have a nice day or a nice evening.
Take care. Bye-bye.
Bye.